Great. Excellent. So, good day to everybody, wherever you are in the world. And I'd like to thank the organizers for inviting me to give a talk a little bit different than our last talk. However, having clean energy also helps your health, right? So, health is very, very important. So, I wanted to give a quick presentation, a brief presentation on what we are doing in the lab. I have many academic appointments that you can see on this slide, mostly based here in the United States. But these days, I love to spin out companies and try to get our technologies into humans. So I created a presentation that will emphasize our human studies and how we're using science, mostly nanotechnology, to improve human health. So, listed on this slide are a whole bunch of logos for the startup companies that have formed out of my university academic lab. And of course, what I need to do at the beginning of the presentation is disclose to you that I have a financial interest in all of those companies. Again, these are typical university startup companies that started with a PhD project for the most part of a student in my lab. We filed for a patent through the university and now they are companies. So through that process, I have equity and ownership in them. So I think a great place to start our discussion here is to think about what's wrong with our global healthcare system. And I think what's wonderful about healthcare is we all have a close interaction with healthcare. Hopefully, all of you go see your doctor at least once a year and find out if you're healthy. What's the problem in your health? So through that interaction, we all know the goods and the bad about our healthcare system. But I want us to think about something that maybe you don't think about too much, and that's considering all of us on this earth together in terms of a healthcare system. So I'm putting up this graph, which basically shows you something that is a little disheartening. And it basically is our average life expectancy over the years. Now, I was born in 1971, so I'm not even on this graph. But for most of my life, and probably most of your life, you have enjoyed an increasing life expectancy. But unfortunately, as we all know, something called COVID came along, and that caused a huge blip, a huge decrease in our average life expectancy. Whether you're talking about your own country, here I have the United States in green, but I also have comparable countries in blue, and then there's other countries in gray. And all of us experienced a decrease average life expectancy because of COVID. In fact, we have really yet to return to the average life expectancy we experienced before COVID. So that's important. But it's also important to acknowledge that in many highly industrialized countries like the United States, some in Europe, like Germany, life expectancy was actually going down before COVID. So we can't always blame COVID for this decreasing average life expectancy because there were problems with conventional healthcare before COVID. And I'm not even talking about the quality of life. It's important to talk about the quantity of life, like we're doing here, but the quality of life is also important to talk about. And there are similar surveys, data that people have collected showing that our quality of life is also going, oops, sorry, is also going down. So clearly we need to address this. And the best way as a scientist to address any problem has come up with a list of what you think is wrong in our global healthcare system. Again, getting away from concentrating on one particular country, but thinking about all of this, all of us in this together. And here's my list of what I think is wrong with our global healthcare system. And I could spend and have spent days in terms of workshops, courses that I've taught at universities, talking about each one of these. and how each one of these bullets we need to change and we really need to overcome if we want to get back to having an increasing quality and quantity of life. So I obviously we don't have that much time here today. So I'm going to start in one area that I've spent my career, and that is medical devices. And something else you might not realize, in addition to our average life expectancy going down in this world, but the other thing that's important to acknowledge is medical devices are an important part to our healthcare system. Artificial hips, pacemakers, diabetic sensors, all of these things have improved the quality of our life. But it's important to acknowledge we don't have any medical device that's used today that is 100% successful. Every single device that we use has some sort of failure rate. And unfortunately, those failure rates for some implants are going up. In the case of orthopedics, we have increasing infection rates. And as you probably know, based on the title of my talk, our conventional healthcare system treats infection by prescribing antibiotics. You get an antibiotic before surgery, after surgery, and unfortunately, bacteria have now developed a resistance to these antibiotics. And we've created bacteria that we can no longer kill with conventional antibiotics. So, what have we been doing? Well, ever since a PhD thesis in my lab that I supervised when I was a professor at Purdue University back in 2002, we have been trying to develop implants that reduce bacteria colonization without using antibiotics. I don't want to contribute to this growing concern of antibiotic resistant bacteria, but instead, I want to try to develop an approach that can eliminate implant infections without using antibiotics. And I'm very happy to tell you, some 20 years later, 25 years later, I think we did it. I think we've accomplished this. Knock on wood that this continues. But over the past 6 years, surgeons, orthopedic surgeons, have been implanting our devices, and one of our devices is a spinal implant in over 45,000 patients here in the United States. It is FDA approved. It's not, these implants are not approved in other parts of the world yet. We're working on that. But here in the United States, 45,000 patients have received these, and none of them have become infected. None of them have failed. They haven't loosened. They haven't resulted in inflammation or scar tissue. They've integrated very well into the spinal bone, and they've returned motor function to these patients. And keep in mind, as I said before, up until this time, we didn't have any implants that were 100% successful. And the industry average for these implants that I'm about to show you is about a 5 to 10% failure rate. And when they fail, you have to remove them, especially if they're infected. You drill out the bone in which the bacteria have now colonized, and you have to start all over again. So incredibly painful, incredibly disruptive to these patients. So we are quite happy and proud of this approach to eliminate implant infection again without using an antibiotic. So what are we doing? Here's three implants. The one on the left is the one that's in the most patients, but all three of these implants have one thing in common. And we have taken these implants off the shelf. Other companies develop them, but what we have done through our startup company, NanoV, there's the logo on the slide right there. We have created a nano texture on these implants. And what we're finding out is when we do that, we are able to keep bacteria from attaching to the implant, growing on the implant, and causing an infection. And at the same time, we're also able to increase bone growth compared to conventional non-nanotextured implants. So what I'm showing you on the left are these spinal screws. We call these pedicle screws. If you have osteoporosis, your spine might collapse. These two discs get weak and they might collapse. If you get into a car accident, whatever the reason that your spine needs a little stabilization, you might get these screws. These screws are made out of titanium. So again, what we've done is we've taken these screws off the shelf. Other people made them, and we anodize them. Anodization is an electrochemical process, and it can create this kind of a surface. Here's a scanning electron microscope image of these nano features that we create on these pedicle screws. And again, when we do that, we see no failure in about 45,000 patients to date. But that's not the only implant that we're seeing success with this approach. We're also seeing success in these spinal fusion devices. So these are larger implants that are used in the spine. Maybe you have more aggressive osteoporosis, or you got in a really bad car accident and you need a larger medical device to stabilize the spine. These are made out of silicon nitride, different chemistry. Therefore, we have a different approach to create a nanotexture. We use laser etching. And here again, you can see a scanning electron microscope image of a laser etched nanotextured silicon nitride spinal fusion device. About 4,000 of those have been implanted in the US and no cases of failure, no cases of infection. The last example is also pretty neat. This is for diabetics. And as you probably know, diabetes is increasing around this world. So more people are being diagnosed with diabetes. The other unfortunate situation, if you have diabetes, you are more likely to get an infected implant, and you're more likely to need an implant in the first place. A lot of diabetics have what's called neuropathy. You lose feelings in your fingers, in your feet, and that means you can't respond to pain, and you might end up with more broken toes and fingers as well as other bones. The other problem, as I mentioned, is unmetabolized sugar, which is very common in diabetics. That is food for bacteria. Bacteria grow in a sugar environment. So you're more likely to have an infected implant and need an implant if you have diabetes. So we started creating this material, a coating on foot screws. That coating is a different chemistry, calcium phosphate, the same chemistry that is your bones are made of. And we created these to be nanoparticles so that they have a nanotexture. And same result. Over 1,500 of these have been implanted in the United States and no cases of infection, no cases of failure. And by the way, if you ever wanted to know how well an implant is performing, the FDA in the United States runs this MAUDE database. So this is a website that you can go on and see for yourself how well these implants are doing. If you're ever prescribed an implant by your doctor, go to this website and see, are those implants succeeding or are they failing? So again, incredibly excited that this approach of nanotexturing implants off the shelf is showing promise for whether it's titanium based, silicon nitride based, or calcium phosphate based. Very versatile type approach. In fact, last summer, we formed a partnership with Medtronic. Medtronic is one of the largest medical device companies in the world. They're actually taking our nanotexture and putting it on their own spinal implant. Here's the packaging of their spinal implant. They call it anatomical nano peak, in which peak is polyether ether ketone, base polymer, coat it with titanium, anodize that titanium to have that same nano texture. So we're about to get a lot more clinical data where hopefully we can positively impact more patients and keep these implants from failing in the body. Now, I don't have too much time to tell you why this is occurring, but obviously I'm a hybrid industry person and academic, so I'm very interested to know, why are these nanotextures improving bone growth but reducing or eliminating implant infection? And really, to make a long story short, it all has to do with controlling protein absorption. Whenever you put an implant in the body, the first thing that happens is obviously water absorbs to the implant. Surface energy changes how much water absorbs to the implant. Hydrophobicity is very important for medical devices. After water absorbs, of course, what comes with water and in bodily fluids are proteins, right? Proteins comes from the Greek word of first importance. So then proteins will absorb in a time scale that you can't even measure. less than a picosecond, proteins will adsorb to your surface. We have thousands of possible proteins in your body that could adsorb. So the types of proteins that adsorb determine whether bacteria attach or not. It also determines whether bone will grow or not. A bone cell, osteoblasts, will attach or not. Or will an inflammatory cell attach? So that protein that adsorbs and how it adsorbs will control how successful your implant is. So all we are doing with nanotexturing, again, nanotexturing any kind of chemistry you want, is we are changing surface energy that controls protein adsorption, which in turn repels bacteria or promotes osteoblast bone cell growth in these cases, or inhibits inflammation or inflammatory cell behavior. And just to show you, of course, we all know this, it's been studied for many different fields, how nanotexturing changes surface energy. Let me show you two videos. This is a 3D printed titanium surface that we created to have a nanotexture that was hydrophobic. And here you can see a water drop that a student is putting on this titanium surface, and the water is balling up. So if we implanted this in the body, we would get hydrophobic proteins to adsorb, and cells will respond or not to some of those more hydrophobic proteins. In contrast, change the surface texture, make those nanoscales longer, wider, deeper, whatever you want to change them, but you can change them, and now you can make your surface hydrophilic. Same chemistry, it's titanium, but here again, you can see the water drop in this case is spreading very well. So this surface is very hydrophilic, very high surface energy. So you put this in the body and you'll get hydrophilic, different proteins to adsorb. So that's all we're doing. Change nanotexture, change surface energy, change protein adsorption, and that can keep your implant from getting infected and at the same time improve bone growth, all without using antibiotics. And of course, this idea is being used in many different industries, many different fields. You know, for windmills, for example, I live close to Boston and we don't want ice to form on our windmills. So make the windmill blades hydrophobic and you can keep ice from forming, right? Put a nanotexture on a boat and you can keep algae from growing. And the idea could go on and on. But here we're just doing it in the context of medical devices. So the other thing I wanted to share with you, because I'm part academic, is how you could do this. If you wanted to improve your implant, your device, maybe you're not even interested in medical devices, but you want to create a surface that is more hydrophobic for your particular application. You want to reduce wear, or you want to, maybe something mechanical you're working on. Here's the steps you can follow to nano optimize your surface. So it's a 6-step procedure. If you do this, I would love to know if it works for you, because we've done this not only for these human implants that I talked about, but we've done this for probably over about 40 different surfaces to show how nanotexturing changes surface energy to improve your particular application. So step one, of course, if you want to work with us, send us your implant. Send me an email and then send me your implant. And then the second step is we have to figure out your starting surface energy. What's the energy that you've created initially? And we use contact angles. They're easy. I understand that there's criticism of a relationship between nano roughness and contact angles, but it works for us. So contact angles, we choose 3 different liquids of different surface tension, measure those angles. Here you can see 2 contact angles that I have illustrated here. We plug those into what's called the Owens-Wendt theory. So the Owens-Wendt theory is one of many theories that can translate a contact angle into a surface energy. Plug that in there and then calculate what your surface energy is. The next 3 steps are a little more complicated. That stuff was easy, the first 3 steps. Step 4 is an equation that we have created, and it's a predictive equation. So this equation right here actually predicts, based on that surface energy, your starting surface energy, which goes in right here in the equation, the E0 comma S, that's your starting surface energy. We can predict with this equation what kind of roughness, what kind of nanoscale feature you should put on your surface to give you the energy you need. So using this equation is how we can come up with the roughness we needed to put on our spinal implants, for example, to make them successful in humans. So how does this equation work? Again, E0S, that's your starting surface energy. So those are the implants we took off the shelf. We know through 30 years of research that a successful spinal screw, if it has an energy of 42.5 millinewtons per meter, plug that in right here, then we can back calculate REFF. That's your roughness, the root mean square roughness that you need to put on the implant to make this equation work. And by the way, there's a factor in here called rho that we have developed, and that rho for titanium is listed right here on this slide, but that rho changes depending on your chemistry. So if it was a polymer, you'd have a different value. If it's a ceramic, it's a different value. Nonetheless, you plug that in, and that helps you determine what your roughness should be to translate from your initial starting surface energy to one that would be successful. So in those spinal screws that I presented, the optimal roughness, if you follow this equation, the optimal root mean square roughness should be 60.5 nanometers, and that's exactly what we created on those titanium spinal screws using anodization. When we did that, we followed in vitro experiments showing that it worked. We, of course, had animal experiments. We got through the FDA, and now it's working in humans. So this predictive equation could be used for really improving any type of implant scenario or surface that you want to change the roughness. But in this particular case, we know the optimal roughness. And step 6 was we just had to come up with a process that creates that roughness without changing the chemistry. And that was anodization. So that's a 6-step process that you can follow if you want to improve your implant for a particular application. And again, we call this nano optimization. If we work with you, we've worked with a dozen companies so far. We give them the stamp that we've nano optimized their surface for surface energy to interact with proteins and therefore to have a successful implant in the body. So I think, unfortunately, I have to stop at this point, um, and not talk about some of the other things we're doing that are in humans. But I hope I gave you a good idea. Let me go to my conclusions. I hope I gave you a good idea of how we can do very simple things like nanotexturing to really improve implant performance. So at least on our list of problems in the global healthcare system, we can remove medical device failure. So again, so happy, cannot believe that, in my career, I've gone from the simple idea to a company to now having human data showing that this idea can really work. So of course, I want to thank the funding agencies throughout all of the years who have helped us get to this point in our research. Most importantly, although funding is very important too, the people. So here's a picture of people in my labs, my companies that really developed the experimental proof that these ideas were working. New books, if anybody wants a free copy, please let me know. We can hook you up with something. And let me just show you this last thumbs up. We have another research direction where we're developing materials that you can 3D print, change their shape, make them beat like this cardiac organoid here with graphene nanoparticles, giving everybody the thumbs up for their interest in science, technology. And if you ever want to collaborate again, here's my email. I look forward to it. So again, thank you for the opportunity to tell you this human data, and I look forward to the rest of the conference. Thank you.